Thank you everyone for coming. Today, talking about how to reduce compilation times through good design. So we'll kick it off. I've got obligatory slide here. So who am I? I'm Andrew Pearcy. I'm an engineering team lead at Bloomberg in the multi-asset risk system department, which we refer to as MARS. A little bit about me. I've spent the last 4 years working for Bloomberg, mainly on their C++ stack. Before that, I have a master in mathematics and computer science from Imperial College London. And I'm here today presenting to you because we managed to reduce our compilation time down from 1 hour to 6 minutes. And so I'm going to talk you through all of the steps we took to achieve that. The fun fact about me is I have kayaked on 6 continents, and I actually led an expedition once. So if you don't have any C++ questions, you can ask me all about that at the end. Okay, diving in. So what are we going to go through? Well, first we'll go through our motivation. Why do we care about compilation times? I'll then do a quick recap of the C++ compilation model so that we all know we're talking about the same thing. I'm going to go through some quick wins. So some ideas, something you can just drop into your code, drop into your toolchain without having to modify any code that might give you some advantages. We're going to look at how we identified the bottlenecks in our compilation, then go through the techniques we applied and the improvement we saw from each of those techniques, and then I'll summarize the sort of the main takeaways and things we learned. Okay. One thing to get out of the way first, this is not a talk on modules. I assume everyone knows what I mean when I'm talking about modules. Please put your hand up if you don't know what modules are. Okay, cool. But yeah, modules are coming. They should actually really help with the compilation problem because of the C++ model being backwards compatible with C. There's a lot of copying and pasting of code. We have one question already. Yep.
Related to the possible to do some of the lighting, does you got code that like that stuff?
That is a perfect point. Can we get the lights dimmed in the front, please? Because otherwise, yeah, all of my slides are going to be very difficult to read. I'll give that 1 second. But I will just keep going on the module front. So the idea is modules should fix this problem, but it's going to be a lot of effort to migrate. You need to rely on all of your third-party libraries as well to migrate before you can do that. So the main issue is going to be what can we do in the meantime in order to actually speed up our compilation before we can fully transition to modules. Obligatory XKCD comic. Who has gone off to get a coffee whilst their code is compiling? Exactly. So our first motivation is we're looking at improving our local DevX. If it's taking a while for you to compile locally, you really have a lot of context switching. You set off your compilation, you go get a coffee, someone interrupts you, you start looking at emails, etc. You lose that context. You then have to try and regain that context to get back into your flow. You also suffer from something I call refactoring inertia. If it's going to take an hour for you to build locally, and then it's going to take another hour to run that on your CI pipeline, and then you got to get someone to approve that as well, just making a small change to improve your code base is, there's a lot of, inertia towards it. So the main thing here is if we can reduce compilation times when you are starting a new project, you can check out, make your refactoring change, get that merged and done quickly, and then actually do your full change without having to worry about your build times. Next thing, speeding up CI. Everyone likes faster CI. With this, I mean time to market. So if you're trying to get new features out quickly, if it's taking hours to compile, that slows everything down because you need to wait for it to compile, you need to wait for all the tests to run, you need someone to approve it. The other one is if you need to hot fix production or anything, then if it's taking hours to compile, then that could actually be crucial if you notice a bug in your production system. Finally, the third sort of motivation is unlocking other tooling. We specifically wanted to look into static analysis. So by that, we're looking at Clang Tidy. Can I run some static analysis over my code base, identify bug-prone things, and just check that I'm using best practices? But the issue is if we're already taking an hour to compile, it's taking almost 2 hours to run static analysis, and that's just prohibitively long. And finally, resource utilization. When you're working in a big company, if I can cut down my compilation times, I need fewer machines in order to actually do all my compilation, cheaper to run, less electricity, etc., etc. So that's why we care. So C++ compilation model, we have preprocessor. By that, how can we actually, can people read that okay? No. Okay, any luck on the lights? I'm going to try one thing real quick. These buttons don't do anything. Oh, is anyone noticing any change? No, this might be a difficult presentation. If you guys can't read the slides, I might just have to read everything out to you. But hey, preprocessor. So hash include directive, pulling in your headers. You've then got macros and defining the meaning of life to be 42. You then have your if defs and your if not defs. And then we get into compilation. So once you have your intermediary file, you do all of your parsing and tokenization on that. And then you do your template instantiation. And then you get into the linking. I'm not really going to talk about linking too much. We're going to focus mainly on the first two phases of this. So coming back to the preprocessor, suppose you have an a.h file. That is really hard to read. If you're going to hash include a string, and then all I'm doing is just defining a class, which is returning a string, okay? Very simple. Sorry, declaring class, not defining. And then in your CPP file, you have the definition for that function. And so you include your header. You're also going to include vector, for example. After you run the preprocessor, your 10 lines of class is going to be 17,000 lines from the string preprocessor directive, whatever you have declared in your header, another 13,000 lines from pulling in vector, and then whatever you have in your CPP. And very much what I'm trying to illustrate here is that the headers and the includes and everything you're pulling in can actually dwarf the size of your source code. So the time spent by the compiler passing through everything and building the abstract syntax tree might not actually be your code, but all of your dependencies. And that's what we're going to come to. On the compilation model as a whole, so we've done the preprocessor side. You get your .i files as your intermediaries. You then pass that to the compiler. The compiler builds that abstract syntax tree, does all the template instantiations, creates the assembly code in your .o files. You then pull in any libraries. The linker steps in, resolves all of that to a single executable, and we're done. Okay? So that's what we're dealing with. But before we do any of that, can we actually modify this tool chain? So what are some of the drop-in things? Well, we're going to look at the build system, the linker, and compiler caching, because these are things you should be able to just modify without having to change your source code. So kicking in with the build system, if you aren't already using Ninja and you have the ability to, so if you're using CMake, I'd really recommend just dropping in Ninja as your build system generator. You can just do -g Ninja in your CMake invocation, and it'll use that build system. It has much better dependency tracking than Make. A lot of profiling has shown that you can almost be an order of magnitude faster than Make when you are doing an incremental build. On a clean build, there's very little benefit. But incremental, actually determining what needs to be rebuilt, Ninja is significantly faster. It is designed to be used with a meta build system. You're not meant to write Ninja files yourself, so it integrates nicely with CMake and a few other tools, full documentation on the website. It was originally written for Google Chromium, I believe, when they were just getting far too frustrated with the amount of time it took for Make to figure out how to build things. And there's a little bit more profiling as well that, order of magnitude, if on a no-op build, it can go from 73 seconds for Make to figure out that nothing needs to be rebuilt, and Ninja can do it in a second. So less time having to wait, figuring out what needs to be built, the better. So that's just a quick drop-in replacement on the build system. Oh, and it uses all available cores by default. You don't have to specify how many cores to use. It just assumes you want to use everything. You can tweak it if you want, but one less thing I have to default. Next up, linkers. Okay, have we had any luck on the lights yet? Okay, I'll take that as a no, but we'll just crack on. I'll just use my voice to talk through all of the code. So, if you aren't already, LLD, significantly faster than a default linker. So if you're using LD or Gold, please do look at LLD. A lot better parallelism and custom memory allocations, which gives it that benefit. And it can be 10 times faster than LD in a lot of cases. Very easy to use. You can create a symlink, or you can just pass -f, use LLU. Wow, I'm already getting tongue-tied at trying to look through code. You can just pass it as a command line argument if you want to. But even more recently, Mold, you can try out Mold as well. It stands for a modern linker, even faster than LLD, written from the ground up by Rui, who also worked on LLD. So he knows what he's doing. Even more parallelism and efficient data structures. The design doc on the website is actually well worth a read because it details exactly the designs that he tried, why they wouldn't work, and the final design he went with. So if you want to learn the internals, very, very well documented. One of the downsides is it is open source on Unix platforms only. I believe it is a paid for subscription service on Mac and Windows. So I apologize if you're on one of those platforms. And the only other potential downside is it does use more memory than LLD. So if you're memory constrained, this does use a little bit more memory because of the data structures it's using under the hood. Quick comparison. So just looking at building Clang with the standard linker, 42 seconds, gold 33. LLVM, we get down to 5, which is pretty nice. Mold is almost 5 times faster than that. So you can just drop in mold and not even worry about it. Linking is solved, maybe. Okay, that's linkers. Next up, compiler caching. Who is currently using compiler caching? Hands up, please. 1, 2. Okay, a few. Great. For those of you who aren't, really recommend Ccache is what we've gravitated towards. The whole idea here is you create a hash of the preprocessed translation unit, the compiler, and the flags that you're using, and you hash that to your object file. And what that means is if you are doing a clean build, ordinarily, you working on a branch, you check out a new branch, all your timestamps are updated, you have to do a clean build. With Ccache, because it's hashed the actual preprocessor of the translation unit, if it hasn't actually changed, it'll just return that directly from the cache, and you can get an order of magnitude speed up on your builds. But yeah, that's one for rebuilds. On incremental builds, generally speaking, you've changed what you're working on, so you're going to have to rebuild it anyway. Ccache doesn't step in. Okay. You can set up a symlink for that, or you can do it as a command line argument, or you can just prepend any invocation you have of your compiler with Ccache. They recommend just letting Ccache masquerade as your compiler, because then it'll just forward everything on. Nice and easy. One nice thing is it does support HTTP and Redis backends for cache sharing between users. So if you have a team of people all working on the same thing, you can set up a Redis cache between all of you. If one person builds, everyone else gets the benefit. If you can do this for your CI pipeline, even better, because then like company-wide, you're getting a huge, huge benefit. The trade-off being is that if you can't set up Ccache for your CI pipeline, there is an overhead for the cold cache because it has to write everything into the cache in the first place. So if you're doing clean builds in a completely new environment, you're not going to want to use it. So it really depends on your use case for your CI pipeline. Okay. That's everything on the quick wins. So just let drop in replacements. So we're going to drop into the case study next.
Yeah.
So as you can see, what we were dealing with, we had a monorepo, building multiple executables out of that. It's about 1,200 translation units, not the largest repo, not the smallest repo. Using CMake as our meta build system and Ninja, you can kind of see why I was suggesting everything beforehand. And compiling with GCC. And when we started out, our build time was about 1 hour, which we thought was a little bit too long for the size of our project. It had been building incrementally over time. I feel like that naturally happens with a lot of projects. The larger it gets, the greater your compilation time gets, until it is annoying enough that you go and do something about it. So what did we do? Well, the first thing you need to do is actually figure out why your compilation time is slow. And this is where I love premature optimization is the root of all evil. I am a big fan of do not try and optimize until you know where the problem is. So how do we figure it out? Any ideas from the audience? How do you figure out what is taking so long in your compilation?
Profiling your build process.
Profiling your build process, exactly. And how do we do that? There's open source tooling. So Clang's ftime trace flag is what we relied on heavily for this. And what it does, it will create a flame chart JSON file of every single translation unit in your build. And as you can see on the right-hand side, you can actually see how that is expanded. You can see which headers it's pulling in, what headers those are pulling in, all the way down to the actual function instantiations through that tree. I do have a quick demo because I discovered the other day that you can do this in Godbolt. So if we're on Godbolt and we're including IOStream, you then have just your square function, and we're just going to print the input, and we're going to print the output. When you run this with ftime trace on Clang 9 or newer, it'll generate a JSON file for you, and you can actually view that. So you got the front end of the compiler, we have IOStream, and then OStream going through iOS all the way down to string, and it'll actually tell you what percentage of the time in your compilation was spent on every single component. So this is where we started to try and actually understand in each of our translation units what is taking the longest time and what is there that we wouldn't expect to be there. There's the original blog post about this, the guy who implemented it. That was where we started. And then you have Clang Build Analyzer, which is another layer on top of the output. And what Clang Build Analyzer will do is take all of these JSON files, figure out, which were your largest targets, what took most time to compile, what headers were included the most, which template instantiations took the longest amount of time, and just generally where all of the time is spent in your compilation phase across the entire project. So you get both the high-level view, and you can look at the individual drill down of every single translation unit. Okay. So this is what our build time evolution looked like. In December of 2022, we decided we had a problem. And we're like, okay, this is too long, guys. Let's try and do something about this. So what we decided is that in our team, we have bi-weekly hackathons where every 2 weeks, we take half a day and we try and improve the system to make our own lives easier. And that is where a good 2 or 3 of us in the team would use those bi-weekly events to try and analyze what the problem was and how do we actually reduce the build times. By April, we'd gotten down to 15 minutes just by applying some of the techniques. And we were reasonably happy with that. A quarter of the time, that's quite nice. And we kind of left it like that for a little while. And then around about August, September time, we took another look at it as like, can we get this even faster? And we got it down to 6 minutes by the time we were done. So how do we do it? The techniques we applied is nothing revolutionary, but just forward declarations, removing unused includes, as I showed with the preprocessor. Even whatever include you have, copy and pasted into your translation unit, the compiler still has to read it and still has to go through it. I definitely have suffered from this where I'll try and write one implementation of a new feature. I'll include, like, say I include the set, and then I change my mind, I'm actually gonna use a map instead, but my IntelliSense has really helped me out and included both of them, even though I'm not using them. So trying to actually determine if you're not using an include, just get rid of it. You're giving the compiler additional work. Splitting protocol and implementation, I'll go through an example of that, but just trying to really separate the interdependencies of your code base. If there's implementations that other parts of your code don't need to know about, make sure they don't know about them, because then you don't have to pass through the same files multiple times. Object libraries, touch on that real quick. Slightly more on the linker side and just sort of less work for the compiler. I'll give an example of that and how we tuned that. Looking at precompiled headers. Is everyone using precompiled headers already? Few? Okay, see a few. If you're not, please do. That one should be very straightforward. And finally, we'll get into Unity build and how we transitioned our project to Unity build. Okay. So, forward declarations in headers. What is it? Formally, forward declaration is when you can declare a class type, which will be defined later in scope, and until that definition appears, the class has an incomplete type. That's the formal definition. Generally speaking, if you don't need to know the memory layout, you can forward declare it, okay? So, what we're looking at is if you have a header file, I'm gonna call it A. I quite like A and B. I'm sorry, I'm not necessarily the most creative person in the room. But if you have a.h, and that includes some large header, because my a.cpp is gonna need that large header, and then you happen to have b.cpp, which pulls in some of the features from a.h, you're transitively including your large header, and so now suddenly b.cpp has to know about this very large header as well, when it doesn't use it, but when you're compiling that translation unit, you still have to pass it, okay? So, with forward declarations, can people read this one? Yes, okay, maybe I should have gone for that sort of font, or sorry, shade. So the forward declaration is my class at the top, okay? We then have another class, which is gonna use that. On line 7, you're gonna have the declaration of a method, totally fine to take a reference or a pointer to that class. On line 8, you can also take an instance of that class as long as you're not using it. So it's fine in the declaration. For member variables on lines 10 and 11, reference and pointer are fine for exactly the same reason. You don't need to know about the size. They have a standard size. And on line 12, you cannot take an instance because you would need to know the size of the object. Line 14, you can return the pointer and use it as long as you're not accessing any of its members and just forwarding it around. You can't return an instance of the new class in the definition because you would need to know its size to actually use it. Line 16, similarly, you can't actually use the class for exactly the same reason when you're doing the definition. You need to know what's in it. And for somewhat completeness, if you're trying to use the incomplete type, so if you're trying to access any members via the pointer or via the reference, you can't do that because you don't know they exist. Okay. So that then brings me on to forward declared headers. Has anyone used iOS forward? Yes. Okay, a good few number of people. For those of you who don't know, iOS forward is literally a header of forward declared classes for IO streams from the standard library. And the idea there is if you have a header, you have a print function or some other function that's manipulating O streams. Within the header, you don't need to know about the implementation as long as you're just taking a reference to the stream. So you can use iOS forward in all of your headers, which means you're not forcibly including the full IO stream header everywhere. You only really care about the CPP files where you're actually going to define these functions. Significantly smaller than the standard iOS header. It is genuinely 128 lines versus 26,000 lines that your compiler has to pass through. So if you're not using that already, I would recommend it in your header files. The other one is consider creating dedicated headers with forward declarations for your classes. Or if you're a library owner, please create them for your library because users of your library can then take the forward declaration as long as they don't need to know the size, and they can actually reduce the amount of times they have to compile and pass through your headers. On that note, there is a Google style guide on this on forward declarations when you should and shouldn't do it. The rule of thumb is very much you can forward declare what you own if you don't forward declare what you don't own. And it is strictly undefined behavior if you try and forward declare anything from the standard library. So don't do that. Okay. There we go. Removing unused includes. This one I always find is a little bit tricky. There is some open source tools like include what you use to try and scan through and figure out if you have any headers that don't actually need to be included. It is a slightly tricky problem. If anyone knows of any better tools, I'm all ears because we really struggled on this one. We tried to write our own. We've had a few issues there, kind of some false positives a lot of the time. So that's one option, is just trying to scan through, get rid of headers. Another one is if you want to do this yourself. If you haven't used GraphViz, you can take a look at that. You can plug it into the CMake API, and it'll generate a graph of all of the dependencies within your project, so you can see what depends on what. And if there's anything a bit unusual, you can drill in and be like, well, why does this depend on that? And that actually helped us identify that we had some cross dependencies from unused includes where things were forcibly relying on other libraries even though they didn't use it. On that note, another thing we found is that we had a lot of code gen via like protobuf for certain types. And generally speaking, when you need to know about the types from another library, we were just including the entire schema for all of those types. And some of those schemas are 250,000 lines long of code that you need to pull in and then pass through every time. And so this is where we came down and said, actually, the more granular you can get, the better for your includes that you're pulling into headers, because you're just trying to reduce the amount of work that you're putting on the compiler for every translation unit. And then, yeah, you're also using GraphViz. So in combination with Clang Build Analyzer, again, getting that visual representation of the dependencies within your code. Is there anything unusual? What are your heaviest includes? What is that dependent upon? Can I break this up a bit so there isn't so much interdependency and all the code is being pulled in everywhere? That's everything on sort of includes and forward declarations. Next up, splitting protocol implementation, which, another favorite quote, can solve any problem with an extra level of indirection. I think that sums up sums this up very, very nicely. So again, the point, nothing revolutionary, but Pimpl, idiom, points implementation, or inheritance. In this instance, you're trying to hide away the implementation so that not everyone needs to know about it. And again, decoupling your system. So get that implementation specific include out of your header. You should only ever need to know about it in one place, and then everyone can sort of try and rely on something more abstract. It also gives you a really nice sort of testing architecture because you can swap things in and out. This is very much where sort of the title of the talk comes from, is that this technique really saved us and just gives you good design as a result as well. Less dependency between your code, less work for the compiler. Everyone wins. Apart from maybe at runtime. We'll get to that. But yeah, we profiled, trying to figure out what are our most include headers. And one thing we found is we have 1,200 translation units, okay? We have this translator, and it relies on a TCP protocol to call out to another service to translate basically on like a hash map idea of things like I have a key, I need to know what this key actually translates to for a given language. And that TCP client was included 500 times throughout our code base. Almost every other file was knowing about it. Here's a quick diagram for everyone. Left-hand side, if you have your large header, so I've got translator on the left-hand side. We have this large header, which is our TCP client, and that needs to be known about in the translator.cpp. Then you have A, B, and C.cpp, which all need to know how to translate something. And they're transitively having to pull in this really heavyweight header when they really shouldn't have to know about this. And so the term, which actually I've seen in a few talks and is referenced on CPP reference, is trying to create this compilation firewall. You inject your interface between A, B, and C and the actual implementation. And now A, B, and C only need to rely on this very lightweight abstract interface, and you reduce the heavyweight lifting to just the only implementation class that needs to know about it. Okay. So this is, okay, I'm going to have to talk you through this. So I mentioned before, we have a TCP client. That is our include, okay? That's quite heavy. We then have a class, which we're going to call label translator. And that label translator has one function called translate, which takes an ID and a language that we need to translate it to. And that's what all of our clients care about, is that I'm displaying messages, I'm auditing something, I need to give feedback to the user. I'm going to take this error message, translate it to the appropriate language, and return it. And what it had is a unique pointer to a TCP client, which we're including. For those who've been paying attention and haven't fallen asleep, we haven't forward declared this TCP client because it's not in a namespace that we own. So in this case, we do actually have to include it because it's not ours. So that's why we're not forward declaring. And so what we did is just split that protocol up, create an abstract class for label translator, where it has a virtual method for translate. It's the only thing it does, only thing it has to worry about, very, very lightweight. And then you create your implementation, which we're going to call a caching label translator. It implements the translate function, and then it holds the pointer to the TCP client. So in this case, now you're doing the abstraction away. Only the implementation needs to know about this really heavyweight class. Everything else doesn't. It can use the really lightweight label translator interface. So what did that get us? So as I said, it was included 500 times. Before we refactored, it took 3.5 seconds on average to pass, and the aggregate build time was 1,500 seconds. So we're spending 25 minutes looking at this file every single time. I was going to say, I should have mentioned actually what hardware I was compiling on. I technically can't tell you what hardware we compile on, but we'll just assume for all intensive purposes that it was a 9th gen i7 with 16 cores and 64 gigs of RAM. And yes, I can't put that in writing. But as I said, 3.5 seconds to pass the include every single time, 25 minutes aggregate compilation time. We got that down to 20 seconds. And so just removed 25 minutes compilation time just by doing a small refactor, because 500 less times having to pass this really heavyweight header. Okay? I was expecting like a round of applause or gasps or thank you. Perfect. So yeah, That then takes us on to object libraries. Is anyone using object libraries? Okay, a few people. So the standard C++ compilation model is you have a file, you have your header, you combine those into a translation unit, you take that, create an object from it, okay? So you have one object for every file. With an object library, what you're trying to achieve is grouping your files together so that you're actually creating one object from a collection of files. The idea being you can reduce some of the linkage time if there's common shared implementations between all of those objects, and just generally trying to create fewer files in general. So one thing we had is 40 individual test executables in our code base. So all of our different test files, each one of those is creating a different object file. Each one of those object files is being made into an executable. And what we noticed is that there's a significant amount of time redoing the same work between every executable and the same linking, because all of these use gtest. All of them have to put all of that in. And so can we sort of deduplicate that work? And so what we ended up doing is with CMake and the add library directive is you can actually merge all your test executables into one. And then you build just one executable, you run that for all of your unit tests, we run that for all of our integration tests, and that took out 2 minutes of linking time just by doing it this way. And so what we ended up doing is that, I'll skip through, yeah, there we go. So on our CI pipeline, we merge everything into one giant executable and run that because we're building from scratch. When we're doing iterative development, we are compiling the individual test executables because it's very likely that you're touching a small part of code. You don't want to have to recompile all of your unit tests every time you're just changing one or two implementation details. So for that, you can make it configurable in CMake. So when on a pipeline, build everything into one executable and run it. When you're doing it locally, we can actually get the granularity that we want to make our lives easier. Precompiled headers. I think I mentioned this one. We did some hands up. So formally, what are precompiled headers? The idea here is you can speed up compilation by creating partially processed version of some of the header files and then stores that in memory, and it will reuse that instead of having to go through the headers again. This was actually added in CMake 3.16. It works very well for headers that are often included and don't change. By this, I mean standard libraries. So you're looking at vector, string, as well as third-party libraries. We decided not to do it for our own headers because we find they're actually changing significantly often. And the issue you get with precompiled headers is you create a target for them. The build system will generate the precompiled headers first because it then gets forcibly injected into every single translation unit. And then you get that benefit of it's already in memory, you don't have to pass through it again. You have the abstract syntax tree. And so instead of having to pass through std vector 1,200 times, you've done it once. So the benefit you get from this is heavily dependent upon how much of these headers are used commonly throughout your code and how much commonality there is between each translation unit. It does require some tuning because if you try and just add everything to your precompiled header, you actually start to get diminishing returns because it gets too large, and then you're forcibly injecting too many things into each translation unit, and you're losing that sort of common shared code that you only have to go through once. I mentioned that. And determining which ones, this is where Clang Build Analyzer can come in because it'll tell you exactly which headers are used and give you the count. And I think you can parameterize it to say how much output you want to give it. Just tell me everything, and it will list all of your headers, how many times they're included. We had, a huge benefit from the standard library headers. The example is quite... So what I'm trying to demonstrate here is that if you have CMake and you have a library that you're creating, which we're going to call foo, and then you have two CPP files, you can then just have target precompiled headers against foo, and you can either just list in here, so we have iOS, functional, string, CMath, and it'll actually generate the precompiled headers for you. So it just creates a CMake underscore precompiled headers.hsx. It'll hash include all of those for you, and then do the representation. You can, if you want to, just write this own file and then target it, whatever suits you. But yeah, just a quick example of how to do it in your project. Some of the gotchas, as I said, less is more. So yeah, as this gets too big, you get diminishing returns. This was a fun one. We discovered that we enabled precompiled headers, and then we tried to compile under Clang, where we didn't have precompiled headers, and it wouldn't build. Reason being, if you have vector in your precompiled headers, and then you have a new source file, and you forget to include vector, it gets forcibly injected into that translation unit by the precompiled headers. So you don't have to include it. Great, I have to include less things, but that's lazy programming, and you're broken your build. So we had to actually go through and fix all of those. And so what we recommend is that on a regular, some sort of regular cadence, just doing a regular CI build or something with precompiled headers turned off, so that you're ensuring that you're not breaking your build.
Yeah.
And we got a 20% decrease in build time just by turning on precompiled headers. A little bit of tuning to try and find the right spot. We started very small. We then started adding third-party libraries, and then we tried adding some of our own, and diminishing returns once we got to our own headers. Some people, depending on your project, might get differences. But yeah, for a quick change, just recompile, list some headers, 20% decrease. I'm pretty happy with that. This is just a visualization of, yeah, the precompiled headers that you're generating up front, you then forcibly inject. One other gotcha with these is that if you change your compile flags, that also invalidates the precompiled headers. Is that you have to ensure that you're using the same flags at the start. And so you do have this now big dependency at the beginning of your build, which could force a recompile of everything. So it's just being aware of that. Okay, so all of those techniques so far got us to April. So we got down to 15 minutes just by forward declarations, splitting protocol implementation, precompiled headers, and then object libraries. And then we left it for a little bit and we went, okay, let's give this another go, and let's try and take this approach of limiting the amount of redundant work the compiler is doing. Let's take it to the extreme, and that's where we come into Unity build. Who knows what Unity build is? Okay, fair number. Who's using Unity build? A few less. Okay, for those using it, I'm sorry, I might not have too much revolutionary for you, but those not using it, you can see what we did. The idea of Unity build is you have your translation units, all of them are using vector, similar idea to precompiled headers, remove the redundant work done, and you're putting those into a library. If you just hash include those files directly into one, you only have to pass through vector once, or whatever header it may be that's shared between them, to create your library. Taking this all the way to the extreme, if you hash include every single source file into one, you only have to pass your code once fully. And so there's no redundant work being done. If you go to that extreme, you then completely lose parallelization because you just have one file to compile. So the thing with Unity build is I think you're really trying to find the right level of granularity. And that's where the default configuration comes in. So you can enable Unity build on your project if you're using CMake by default. If you just say enable Unity build mode, true, 1, whatever, and it will default to a batch size of 8. And what CMake generates, which you can't see, is just a file that hash includes all of your files. So we have widget, we have component, we have my database accessor just hash included into one, and it will bulk those into 8 files at a time. One, so that you don't have too many files in one go and could eat up your memory a bit more. But 2, you still want to get some parallelization. If you, in theory, you can enable Unity builds, your project compiles, everyone's happy. If that works for you, I'm very happy for you. That didn't work for us. The first thing we noticed is anonymous namespaces, each translation unit, anonymous namespace, nothing is accessible outside of that translation unit. Well, now you only have one translation unit, so your anonymous namespaces are no longer anonymous. And so if I have print in one file and print in another file, well, that's now a compiler error. And you have a few options. You can go and rename all of your functions that clash. You can rename all of your anonymous namespaces and reference them to the file if you want to. But thankfully, CMake with its Unity build built in gives us something called Unity ID. And so you can actually specify this in your CMake on a per library sort of level. So we specified ours as Unity ID. What it does is it puts a unique namespace in for you. And so you no longer get the clash between all of your symbols. There is a little bit of annoyance because depending on how much you're using your anonymous functions within, because you're now in one translation unit, you would need to append the calls with the unique Unity namespace. This is something that can just be a little bit of annoying work to do on a late Friday afternoon. Or we experimented a little bit with trying to use Clang Query to try and replace and get this in. Didn't quite get it working, but got something almost working to do it. So there's options. This is just going to be a quick talk through, again, which you can't see, but in the CMake, you can set the target properties to say, for whatever my target is, I'm defining a Unity build unique ID, and then what that actually does under the hood is when each CPP file is hash included, it defines a unique Unity ID and then undefines it. Nothing magic going on, but that's what it's doing under the hood. Next up, build template instantiations. Template instantiations for Unity build. So much talking because you cannot read the slides. I will bear this in mind for next time. Yes, sorry. A question. Oh, we'll get the mic.
We also had the problem, as with the anonymous namespace, with static variables.
Yes,
because they also then are doubled.
Yeah.
It doesn't compile.
Yes, exactly the same issue. But yeah, that's, again, you can solve the same thing, put it within a named anonymous namespace. It's annoying, but yeah.
Oh, no, but
Thank you. Oh, another question? Yeah.
Another thing that is a problem is that we usually in the CPP file also using namespace because we use namespaces and then we should start to use namespaces in all the CPP files that you put in your Unity build you get in.
Yes, yeah, that is an annoyance. So this is kind of, I think, the issue we ran into as well, is if your code base was not initially written to be Unity build compliant, it is surprisingly difficult to convert it to a Unity build. But yeah, thank you. Cracking on template instantiations. So what we have is a header file where I'm going to have a templated function that takes a vector of type T, and I'm going to do something generic with that. And then in my CPP file for that, I'm going to use a template, and that's just going to call my generic function. Everything's fine. And then in another file, I include the template because I might need to know about it. And then I'm going to have a specialization of that function. So I'm going to now do something specific for a vector of ints. And then I'm going to use that specific implementation and try and apply the function to my vector of ints. And once again, the compiler will complain at you because depending on the order that you include these files, you are trying to specialize a template after it's already been instantiated, which is disallowed. So one option is you can just reverse and lexicographically order your files in the name they need to be included. I'm not sure anyone's happy with that. But there is a solution, which I'll come to after one more example. Template overloading. So here, I'm going to have a print function, which is going to take a vector of dates, and we're just going to print out all of those dates on the same line. But we also happen to have a templated class of print anything, which is going to print all of my vector of t on the same line with commas separated. And this will compile perfectly happily, but it'll change your implementation because now you're hitting the specialization for dates, the exact function for dates rather than the template. And there's no safety around this. Compiler's perfectly happy to do this. The only way we notice this is we have tests around the audit logs for when we're changing things. And we suddenly noticed our tests were failing because the output format of the audit log was different because we had two different ways to print a vector of dates. So that's the one I really want to beware people of, is that you could change the underlying implementation of your code and you wouldn't know. So what can you do about it? This, I'm going to skip. Nah, I don't want to skip forward. Okay, slightly out of line, but we'll come back to it. So I'll talk you through third-party libraries. Again, I'm going to continue reading out code from the board, but we have a struct component we have an enum. That enum has a widget, and it has a pulley. I'm sure you can guess where I got my inspiration from. We then have our Unity file, which includes one file a.cpp that pulls in some other headers. We have b.cpp, which pulls in our component. And then we get a wonderful compiler error. Can you read that one? Yes, maybe. Red is a better color. Expected identifier before numeric constant widget. And this one actually threw me for a while because I wasn't too sure what was going on. Does anyone have any guesses? Okay, that makes me feel a little bit better because I was quite stumped by this for a while. So I went back and looked at component. Okay, component is a third-party library. I look into there, we have widget. Widget is perfectly defined as equal to. Is something redefining widget somewhere? So I start going to look into all of our third-party libraries. Do we have another enum declaration for component defining widget? And I finally broke down and went, okay, let's just run the preprocessor and see what's going on here to try and get some insight. And this is when I had that the enum value, it gets replaced with 7 equals 2. And this is when I looked at it and I was like, I can see why the compiler is complaining. I can also now see why the error message is so vague, because it's pointing at the source code issue, but the preprocessor has manipulated that. And I went and spoke to someone, I was like, well, surely we'd want the post-processing output so we can actually see when this replacement is done. And I realized that was a terrible idea. But the main takeaway here is that macros are really annoying. In that in our products in a separate third-party library, you have a macro, it defines widget as 7, and as soon as you combine these two third-party libraries, they are completely incompatible. So that was a fun afternoon figuring that one out. And what are your options? You can either not use these two third-party libraries together. You can try and go to the third-party library owners and say, hey, can you change that? Good luck with that one. Or you can actually use what you make thought of, which is how do you isolate specific files that are known not to compile together? And you have a few options. So coming back to the macro invocation, as well as the specialization where you're changing the code implementation underneath without knowing, is that CMake will actually let you skip Unity build inclusion on a per file basis. So you can just specify that, hey, for this file, I don't want it to be in my Unity build. It is just going to be compiled separately, okay? And then you get the isolation that you previously had. Cool. The other option is you can group files together via Unity group. So by default, CMake will just take 8 files, lexicographically mash them together. If you want to, you can manually specify. We've done this in the case with the third-party libraries because we kind of knew that this set of files is using that third-party library, this set of files is using that one. We'll force these to be compiled separately because they should share a lot of the same code as well. So if you have some insider knowledge on how you're compiling and what's likely to go together, then you can use that. So what were the results? I spoiled it a little bit already with the graph, but when we got to Unity build, we had 1,200 1,200 translation unit. I think there's a slight typo there. Took 15 minutes to build. When we enabled Unity build by default, batch things into groups of 8, creates about 240 targets, and we got down to 9 minutes. And then if you just set Unity build to infinity, so for each of our libraries, just shove everything together, we got it down to, again, a typo. Wow, I'm doing well. 6 minutes, not 7 minutes. So that's when the factor of 10 comes in. But the other thing that we noticed is I mentioned way back at the beginning that we wanted to try and unlock static analysis and try and apply Clang Tidy to our code base. And it was taking about 2.5 hours when we started. Well, when we got the compilation down to 15 minutes, we're in about 40 minutes for Clang Tidy, which is okay. But then doing it with Unity build, it took 4 minutes. And this is the one that actually surprised all of us. And we thought about it for a while. And the only thing that kind of makes sense is that if you think we're a factor of 10 different on number of compilation targets, we're pretty much a factor of 10 faster. Because for your static analysis, you don't have to worry about any of the linking or anything. You are just completely cutting down the number of headers you're including because you're not having to pass them additionally. And so as long as your includes dwarf the size of your source code, I reckon you can get sort of similar relative speed up to this. But yeah, that takes us to 55% reduction in build time and up to 90% reduction in static analysis. So we can actually use static analysis now. Couple of considerations on a Unity build. You might not get a benefit for incremental builds, because if you're slamming all of your source files together, creating larger translation units, if you're just changing one thing, you have to recompile the entire thing. It's a little bit annoying. That's when it depends on the Unity group build size. Choose your granularity. How much do you want to build together? The next one is clean builds will benefit the most because you're building from scratch. You have nothing. Whilst in the iterative build case, we made this configurable. So when we're building on our pipeline, we do a Unity build. It's faster, run RSAT. When we're building locally, because we don't want to have to suffer that incremental build sort of issue, we actually tend to build in the old school manner of individual targets because we're touching fewer things at a time. Same thing as precompiled headers. You can break your regular build with Unity build because transitive header includes from putting everything together. Again, same recommendation as precompiled headers, just on a regular basis, make sure you're doing a regular build so that everything is happy. You can run into ODR issues and other build incompatibilities, so a little bit wary or see how much time it takes. And if for whatever reason you don't want to do Unity builds or it's too much effort, my general advice would be try and reduce the number of files you have. If you have lots of small files, you're trying to compile those in parallel. If they're, again, pulling in all of the standard library or just sharing any components, fewer larger files are better than lots of little ones. So that's just the general idea. That takes me on to main takeaways. So just a quick summary of everything we've been through. Just first thing, profile your build. Don't start trying to reduce your compilation time before you know where the time is actually spent. Forward declarations, I'm going to say it sort of reduced our build time by 60% with an asterisk because it was in combination with removing unused includes and in combination with splitting protocol implementation, just trying to remove the interdependency between all of your code. Merging executables, got about 10% difference on that just by not having to do additional link time. Tuning precompiled headers, 20% difference on that, really easy, drop in replacement. Very little can go wrong with that, in my opinion, very safe. And then 50% reduction with Unity builds, but there is a small risk, just to be aware of. That, I think, is everything I have for you. I have rushed through that very quickly. The only other thing I would say is just thanks to my teammate, Dallas Clement, who I worked very closely on this project with, and to the entire team of people I worked with, because it was a big team effort over time. And that's it. Thank you.